All right, I hope you can hear me properly and see me properly. So welcome back. And today we're going to start our discussion on state space analysis. All right. So this is not going to be similar to what we have been discussing so far. Okay. So far we have been discussing transfer function, so analysis using transfer function, right? So we have learned quite a bit on transfer function modeling and different analysis techniques related to transfer functions, right? And today we are going to deviate from that. We are going to basically change our ideas, change our discussion completely. So we are not going to build upon what we have discussed so far. So this is a completely new discussion, rather, I would say. So I'm going to point out the shortcomings of transfer function analysis, and then from there we are going to actually build up the state space analysis techniques. But don't worry, there are a few more things that we need to discuss that belong to the transfer function analysis techniques. So essentially there are things that we haven't yet discussed. Okay, so we are going to actually go back and forth between transfer function modeling techniques and state space analysis techniques. And very soon you will learn that if you have the state space model, okay, you can easily construct the transfer function model, okay, for a linear time invariant system. Also, if you have the transfer function, you can also construct the state space model. So yeah, these two are interchangeable in nature. All right, so let's talk about, before we actually talk about state space analysis in general, let's talk about why we need any other type of analysis technique, or rather any other type of modeling technique, first of all. Okay, so when we write analysis, of course, we discuss the topology of how we actually discuss how we actually do control system engineering in general, right? We first of all try to figure out a mathematical model of the things that we are actually trying to control, right? So of course, one of the mathematical modeling techniques is known as the transfer function modeling technique, in which we actually construct the transfer function of the system, and from there we actually describe different behaviors, and from that we analyze what kind of control scheme might be useful for that, and from there we actually develop the controller. So that is the idea in general. Okay, and that same idea applies here as well. So when we talk about state space analysis, the first thing we need to talk about is state space modeling. Okay, so if we are given a system, okay, if we are given a system, how to describe it mathematically using the state space terminology. So idea is that how to do a modeling of the system, how to model the system in state space. So that is exactly the first step in doing state space analysis, and this is exactly what we are going to learn today. All right, so the first part of this analysis technique is modeling, right? So we need to actually construct the model, mathematical model of the, or mathematical model of systems, dynamic systems, right? Important thing to note here is that sometimes we do encounter systems that cannot be modeled mathematically using transfer function approach, using the transfer function approach. Okay, so let me just give you the scenarios under which let me give you the conditions which need to be satisfied in order for a transfer function model to actually exist. Or whether or not you will be able to construct a transfer function, that's a different issue. Okay, but the conditions under which a transfer function model would exist for a system are these. Let me just write it down. Okay, okay, so if I want to do transfer function modeling, these are the conditions that we actually encounter. Rather, these are the conditions that must be satisfied by the system itself in order for a transfer function model to exist. So number one, the system has to be linear. So if the system is somehow non-linear, a transfer function model cannot exist. Okay, because if the system is non-linear, then the differential equation involving describing the system would also be a non-linear differential equation, and thus we won't have that simple expression on x and y on both sides. So you won't be able to take the ratio of the Laplace transform of the output to that of the input. That wouldn't be possible. So having a nonlinear system immediately ensures that we don't have a transfer function of that. Okay, so the system has to be linear first of all. That's the first condition. Then the second condition is that the system has to be time invariant. There cannot be any explicit time dependency, right? So because if there are any explicit time dependencies, then once again the same thing happens. We don't have a polynomial expression on x or y. Okay, on either the input or the output, wherever we have a time dependent term. Okay, so the system has to be time invariant. So instead, let me just write it at once. The system has to be linear and time invariant. So the system has to be an LTI system. Okay, if the system is not LTI or any one of these is violated, if the system is nonlinear or if the system is time variant, under these scenarios, the transfer function model cannot exist. Okay, so that's the primary concern here. Okay, then a few things are there associated with this. There are imposed conditions. For example, even if the system is linear and time invariant, okay, and so the transfer function model can exist, then there is a problem. Okay, if there are initial conditions, then for example, we know that if we want to take the Laplace transform of the derivative of something, like for example the first derivative of yt, if I take the Laplace transform of this, and if I know the Laplace transform of yt to be ys, then the Laplace transform, the first derivative of yt is gonna be sys minus y0. Now remember, this is in the time domain, so this is called the initial condition. Now these kind of terms will be there if we consider the initial conditions, and that will pretty much make sure that we cannot express the ratio of the output, Laplace transform of the output to that of the input in this way. This is not possible. That's why the Laplace transform, the transfer function approach requires that the system exhibits zero initial condition. Okay, so we don't have these initial conditions. Okay, these terms are not there. So that is kind of the imposed condition on this in order to generate a Laplace transform, generate a transfer function. Okay, so the condition is that the systems must have zero initial conditions. Now these three things, okay, three things: linear, time invariant, and zero initial conditions. These three things taken together might seem like a small set of conditions that we are imposing. Okay, but in reality, if we want to actually, if you actually look at any physical system and you want to make a mathematical model of that, it is highly possible that you will find out that the system that you are modeling is maybe nonlinear. Okay, many physical systems are actually nonlinear in nature. So it is very highly likely, it's quite highly likely that you would encounter a system that is nonlinear. So transfer function modeling will not do. Similarly, you might find a system which is time variant, okay, which changes with respect to time itself, with the parameter of the system actually changes with respect to time. So then the transfer function modeling is not a feasible option. Okay, and then we need to have zero initial conditions imposed. And sometimes what happens is that the systems do have initial conditions, so we cannot assume zero initial conditions always. Okay, or any mix and match of these violations. Okay, if any of these are violated, then we cannot construct a transfer function model. So this is you have to remember. Okay, if any of these conditions are violated, then we cannot construct a transfer function model. But then there is another condition that we actually impose manually in order to make sure that the model is actually usable in some sense, right? All right, just hold on for a second. Well, someone please inform your classmates in your WhatsApp group to join, okay? Those who are attending the class right now, please inform your classmates in the WhatsApp group to join the class. Please share the link. Right. All right, so zero initial conditions are imposed, and then we have an additional condition that is for making sure that the model we develop is actually useful, and that condition is that the system has to be single input, single output. Okay. So, okay, try to remember that these two are conditions. Okay, these two are conditions, and the idea is that if any of these conditions are violated, then we don't have a transfer function model at all. Okay, so these are conditions, and if any of these conditions are violated, then the transfer function model does not even exist. But if the system has more than one input or more than one output, or if a combination of both, more than one input as well as more than one output, in that case the system is called a MIMO system, multiple input multiple output system. And there we don't just have a single transfer function describing the system, we actually get a transfer function matrix, and the transfer function matrix describes the relationship between every possible input to every possible output. So we get something called the transfer function matrix. Okay, this becomes the TF matrix. So instead we get the transfer function matrix. Okay, so this idea is really, what should I say, difficult, and we have different pretty big transfer function matrices, right? For example, if we have two inputs and two outputs, then this becomes a transfer function matrix that has 4 elements in it. So essentially we are dealing with 4 elements, 4 different transfer functions really, right? So again, similarly, I assume if I have 3 inputs and 2 outputs, then we have a transfer function matrix that has 6 elements in it, right? So literally speaking, we are actually dealing with then 6 different transfer function, one transfer function relating one input to one output, right? So that's the idea here, and that's how transfer function modeling easily becomes very difficult to work with. So the very idea behind transfer function modeling was that it will simplify our analysis, but eventually what happens is that it actually becomes very difficult if we have a single input single output, if we have anything other than a single input single output LTI system. Okay, so in general, transfer function approach is a good way of dealing with things if we have a CISO LTI system that can be considered to be having zero initial conditions. Okay, again, CISO is not a condition here. Okay, having a single input single output system, that is not a condition. Okay, but if we have that, then actually the transfer function is usable rather. So if we have multiple transfer functions leading to the say describing the same system, right, at the same time, okay, relating different inputs to different outputs of that system, then it becomes a mess, really mess. Okay, so we don't really want that. So again, if we have a MIMO system, we have a transfer function matrix, and this is not desired. Okay, all right. So if any, you understand by now that if any of these conditions are violated, then we don't have a transfer function model, then we need to look for another modeling technique, and that is exactly what Radloff-Kalman did. Okay, remember the name, Radloff Emil Kalman. So he is quite literally called the father of modern control engineering. So he pretty much invented what we call modern control engineering. Okay, so in the classical control techniques, what we used to do, we used to approach it through the transfer function way, right? In the transfer function way, and there are several ways in which we actually use the transfer function technique. We are going to learn quite a bit in the future as well. But in the modern control technique, so this is called modern control. Okay, now this term modern might is pretty much relative here. Okay, back then it was modern because it was developed in 1950s. Okay, late 1950s. Okay, so it was developed in 1950s. Okay, late 1950s rather. Okay, So around 1956, 1957. Okay. And if you recall that most of the other things that we have discussed so far, like the transfer function related techniques, those were developed earlier than that, at least 10, 15, 20 years earlier than this, right? So when Kalman was working on uh, developing mathematical models, developing certain different types of controllers for particular systems, he realized that often we cannot use the transfer function approach, or rather it becomes really cumbersome if we use transfer function approach, right? First of all, if we are dealing with nonlinear systems, we cannot even talk about transfer function approach. So he pretty much developed a way in which there are certain things that were already known in the realm of mathematics. Those who are actually studying mathematics, they already knew some of these things. Okay, so he actually brought them in the engineering domain. Okay, so for him, we actually know how to deal with these things in a more elegant manner. So discussing the modern aspects of this, or this modern aspect is essentially talking about the state space analysis technique, state space modeling technique. So let me just write down. Regarding the spelling of modeling, if I'm using the British spelling, then that's going to be MODELLING, and there'll be a single L if I'm using the American spelling. Anyway, so he developed the state space modeling technique, and back then it was the modern control engineering. Okay, modern control technique. Okay, and I referred to the book by Ogata. Okay, so the name of the book itself is Modern Control Engineering by Katsuhiko Ogata. So that is the name of the book that is the book we actually refer to, right? So Kalman actually developed many of these techniques. Okay, many of these techniques, and he pioneered state space analysis, state space modeling techniques. And nowadays, the thing is, if you are actually doing anything useful in control systems, in the domain of control systems, it is highly likely that you are not using transfer function approach. You are using the state space modeling technique. Okay. The idea is that if these conditions are satisfied, then we have a transfer function. Not a problem. But developing a state space model does not require that we satisfy a particular condition. Do we have a nonlinear system? No problem. You can construct a state space model. Do we have a system that is having a time variant? Not a problem. You can have a state space model. Do you have a system that has non-zero initial conditions? Not a problem. You can have a state space model. Okay. Do you have a system that has many inputs and many outputs? Not a problem. The same state space model can handle them very easily, okay, without making the things unnecessarily complicated. Okay. So idea is that if we have even a complicated system, very complicated system that cannot be handled at all by transfer function approach, okay, the state space modeling technique can work. Okay. So the thing is, if these conditions are satisfied, then that's even better. Okay, if these conditions are satisfied so that we have a transfer function, then it is even better. Okay, the idea is that then we would definitely have the state space model as well. So the idea is very simple. If we can construct a transfer function model, okay, if we get a system that has a transfer function, then that definitely also has a state space model. Okay, but it is not the other way around. Okay, there are systems for which we would be able to construct the state space model, but those systems not necessarily, it is not necessary that those systems are gonna be having transfer function models. Okay, you understand what I'm saying? So if we have a system that can have a transfer function model, then that will also have a state space model. Okay, but it is not the other way around. There are many types of systems that are maybe non-linear, maybe time variant, maybe having initial conditions, non-zero initial conditions. Okay, for which constructing the transfer function model will not be possible. But for those systems, we shall have the state space model. Okay, so that's the idea here. State space modeling is pretty much universal, and if you are actually ever doing any real work in the domain of control systems, you would see that state space modeling is the way to go. Okay, it might seem slightly difficult and slightly different from what we have done so far, but this is gonna feel like the easiest one under the hood. And all modern software that you use, namely MATLAB, Scilab, and Python, that you can use to actually do modeling and analysis for control systems, those actually under the hood use this state space model. So even if you are asking it to deal with certain transfer functions, okay, and construct the solutions of systems and etc., it will actually under the hood, behind the scene, it will actually convert everything to equivalent state space, or at least some representation that is very similar to state space, and then actually try to solve it. Because state space, the state space modeling technique, the state space analysis is so systematic that there are no ad hoc ways, right? For example, if I give you a transfer function and ask you to figure out the inverse transfer function, okay, sorry, I mean the inverse Laplace transform of that, so that you get the impulse response, or something like that, then you pretty much hammer it, right? Hammer it until you get a solution, right? You pretty much try to figure out what to do at this point, and then you, if you can find out some similarity with something that you know already, you express it that way, and from there you get an inverse Laplace transform. That's how you deal with transfer functions, right? So it is pretty much like a brute force technique in many cases. So transfer function approaches and different techniques related to transfer functions do require some amount of brute forcing, right? Some amount of trial and error, okay? Some amount of manual effort there, okay? But regarding state space modeling techniques, it is so systematic in nature that it is very usable and very easily implementable using a computer program. Okay, so in the earlier days, people, or rather us, we didn't have computer programs that could deal with transfer function models, but we did have computer programs that could deal with state space models. Do you understand what I'm saying? Okay, the earlier computer programs, like of course that came quite a bit later than this, okay, could not deal with transfer function models. They could only deal with state space models. The earlier mathematical models, the earlier computer programs. Now you understand how easy it was for computers, right? So this is so systematic that it can be used in computer programs. So keep that in mind. And that also brings one difficulty. So whenever something is very systematic and can be easily implemented using a computer, it might sometimes be very laborious for a human being for manual computation. So if you're doing manual computation, this sometimes might feel very difficult. For example, if I give you a 3 by 3 matrix and ask you to take the inverse of that matrix, for a computer it's really easy, right? It is not even a challenging task. But for a human being, it's difficult to invert a 3 by 3 matrix, let alone if I give you a 4 by 4 matrix. If I give you a 4 by 4 matrix and ask you to take the inverse of the matrix, for a computer it's really easy, but for a human being it might be difficult. But the thing is, whatever we do, we have a very concrete system. We have a very systematic way, a systematic approach, okay? And if you follow the approach exactly, you will end up with the correct results without any issue. One thing I must note though, that for in the state space analysis, in the state space realm, I give you one unique system, okay, and consider that system has a transfer function, right? If I give you one unique system that has one unique transfer function, okay, but that would have infinitely many state space models. Let me repeat, a unique system that has one unique transfer function, okay, would have, not can have, but would have infinitely many equivalent state space representations. A unique system that has one unique transfer function would have infinitely many equivalent state space representations. So the state space representation is not unique, okay? It should cater to what you need, okay, in particular. But there are different state space modeling techniques and different ways in which you can represent the same system. So a single system would have infinitely many state space models. Just keep this thing in mind, okay? All right, so right now we are going to approach it in a way which is called the which is one of the canonical ways, one of the standard ways in which you can actually deal with this. All right, let's imagine we have a system, okay? Let's imagine we have a system, and for the sake of simplicity right now, let's assume that it's a linear time invariant single input single output system, so that it has a transfer function as well, and pretty usable transfer function, okay? Let's say the input is being defined as, let's say the input is being defined as ut, and of course it does not have to be a unit step, it's just some input, and the output is, for example, let's say, okay, let me use the proper terminology here. The input is the reference, and the output is the controlled output, the controlled variable. Okay, and this is the system. So this is a CISO LTI system. All right, CISO LTI system. And of course, we know that the relationship, if it's a dynamic system, of course, the relationship between C and R is actually a differential equation, right? A differential equation. So C is the controlled output and R is the input, right? So let's say that the differential equation pretty much looks like this. Let's say the differential equation looks like this. Say it's an nth order differential equation, okay? And it looks like this: A n and so on. Okay, of course, C is a function of time. And very similarly, we would have, so it's an mth order differential equation on the other hand. All right. So this is the differential equation. Imagine this is the differential equation that is describing the system. All right. So it is not a problem. We actually have encountered this sort of differential equation. Now let's understand that this differential equation is an nth order differential equation. Okay. Right. So this is something we already have seen, right? We already have seen. So the idea behind this is that we now, so this is an nth order differential equation, and of course we say that n is greater than or equal to m, okay, for standard systems here. And we of course discussed why this is necessary, and we shall actually discuss a little bit more on this, right? So now of course, if this is a linear system, of course we are assuming a linear time invariant system, so these are constants, okay? So if this is a linear time invariant system, these all coefficients are constant, so all these are constants. So a1, so rather a0, a1 up to an, and b0, b1 up to bn, these are all constants. Okay, so it means they are neither functions of time nor functions of the input or output. Okay, so that is the idea. Now of course, if you could apply the Laplace transform on it, assume zero initial conditions and go in the way of transfer functions, but here we're going to stop. Okay, here we're going to stop. We are not going to go that route. In that route we are going to actually take a different route and not assume zero initial conditions. Okay, So I'm assuming a CISO LTI system, but I'm not assuming zero initial conditions. Instead, I'm going to assume non-zero initial conditions that are not necessarily zero. Okay, so that we don't have a transfer function. Okay, we don't have a transfer function. But later on, you will see that we could still assume zero initial conditions whenever we wanted to. Okay, that's the idea here. Okay, so we are going to actually generalize our model, and then we can impose whatever conditions we need at that particular point, and we will still get the correct results without any difficulty. Right. So if this is the differential equation model describing the system, then there are certain standard terminologies that we need to understand right now. This is an nth order differential equation. The highest order of the derivative in this is, of course, n, the nth order derivative, right? So this is the highest possible order. It could also be the highest possible order if m and n are equal, but we are saying that n is a larger number than m. So that way, the differential equation is an nth order differential equation, right? So, and that is the definition of the order of the system, and you already know that the derivative order of the output actually determines the order of the system. Okay, so in the transfer function model, if we construct the transfer function model, in the denominator we shall have s to the power n. Okay, so the system would be an nth order system. Okay, so this is an nth order system. Okay, all right, that's an nth order system. Now, to make sure that this discussion is not that complicated and I don't write some gibberish that you don't understand, okay, let's make sure that this is a very simple discussion, and let's simplify this, and from that we are going to actually develop some more complicated discussions, some more complicated systems here. Okay, let's say that the system that we are describing is a very simple third order system, let's say. Okay, and the differential equation now kind of looks like this. All right, so that's the output side. Let's say on the input side we just have the input, so there are no complications here. So that's the differential equation describing the system. So let's say this is an example. Okay, and again we are taking this example to make sure that the discussion that we are having is not unnecessarily complicated. All right, so let's say this is the system. So this is a very simple third order system, and of course if we assume zero initial conditions, then we can actually write down that the transfer function, which is Cs by Rs, okay, which is going to be 1 by a cube s cube plus a2, so a3 s cube plus a2 s square plus a1 s plus a0. Okay, well, that is the transfer function we're going to have. So that is something we already know, because we are assuming a single input, single output, linear time invariant system. So this is a very simple example for that matter. Okay, and again assuming zero initial conditions here. Zero initial conditions. Okay, so assuming zero initial conditions, we can actually, so this is again a CISO system, LTI CISO. Okay, it's a very simplified example, right? So that we actually get the idea of what we are saying here. Okay, remember C and R, these are all functions of time, which we are not actually writing it down explicitly, but these are all functions of time because these are inputs and outputs, right? So these are all functions of time. R is the input and C is the output. Now, before we proceed and do anything with this, the goal of state space approach or state space modeling technique is to convert this third order differential equation into a first order differential equation. Let me repeat. The goal of the state space approach or state space modeling technique is to convert this differential equation, which is currently the third order differential equation, or maybe to convert this differential equation, which is an nth order differential equation, into one first order differential equation. And you might say, what? How is that even possible? Okay, I have a third order differential equation, and how can I even convert that into one first order differential equation? That is possible by doing some, bringing some techniques from the domain of linear algebra. Okay, we are going to do that shortly. Okay, so the goal or approach when we use the state space modeling technique is to convert this nth order differential equation into one first order differential equation. Okay, that is the idea. But how do we do that? Okay, how do we do that? So once we convert it to one first order differential equation, then we have successfully completed the state space modeling. Okay, that is the goal here. So in the state space model, we convert this to one first order differential equation. So let me just write it down. Convert this to one first order ordinary differential equation. Okay, that's the goal, that's the objective here. Okay, that's the objective of state space modeling technique. And you might think that this might not be possible, right? It's a nth order differential equation. How can you even think about converting it into a first order differential equation? You will soon see that we can actually do something that resembles what we are just saying here. But before we proceed, there are now time for some name changes. Okay, some name changes. Keep in mind that these name changes are required to make sure that we kind of have a coherent discussions, so that we can actually follow any material on this. So these are the names that were chosen by Kalman. So we respect him and we actually write down the names accordingly. Okay, all right, not a problem, right? I hope. Okay, so we usually write C as the signal representing the output, but here we are going to not use C to represent the output, but instead we are going to call it Y. Okay, so Y is going to be representing the output. Okay, Y is going to represent the output. Not a problem, I hope. Okay, similarly, we usually write R to represent the input. Okay, and here in the state space terminology, we are going to use YT. Y is, U to represent the input. Okay, so these are again standard terminologies, and nothing will change. Nothing much will change. So if I now write down this differential equation, then this simply becomes, instead of C, I would have written Y, and instead of R, I would have written U. So let's do that. Okay, so that's the differential equation. So do you have any difficulty understanding this right now? I hope not, right? So let me just write down the differential equation. So I have A3 and the third derivative of Y, because I'm just writing C equal to Y, right? So I'm just calling them with different names. And there is one more thing. Since it's a derivative, I can always use dots to indicate that's the third derivative. Okay, any problem there? 3 dots indicate that it's a third derivative. Okay, then I have A2 Y double dot, then I have A1 Y dot, then I have A0 Y. Okay, and on the right hand side I have U. Remember, all these are functions of time. Okay, U and Y, these are functions of time. A0, A1, A2, A3, these are not functions of time. Okay, but everything else is functions of time. And let me just do one thing. Why not? Let's put a B0 here, so that I have a B0 here. All right, let's put a B0 here. Okay. So no, not yet. This is not yet a first order differential equation. This is still a third order differential equation, right? And now we are going to do some substitution. Okay, some substitution. So now let's talk about the state space substitution. Okay, so in the state space substitution, we do some important substitution that actually can convert this differential equation. So this is the third order differential equation. So we are now going to do one substitution that can actually convert this third order differential equation into 3 first order differential equations. So converting this nth order differential equation into n number of first order differential equations. Okay, so the substitution is very simple. We consider a variable x1, okay, and we assign it to the output variable. What is the output? Yeah, that's y, right? And there are two more things. We need to consider another variable x2. Now, these might seem ad hoc right now, but these are very standard, okay? And that will be assigned to the first derivative of y, and which is in turn becomes the first derivative of x1. Again, these are just assumptions. So we are going to do substitutions, okay? And we are going to assume another variable x3, which is going to be the second derivative of y, which is the first derivative of y dot, which is the first derivative of x2, which is the second derivative of x1. Okay, this is, I think this is understandable, right? So the derivative, so y is there, right? The derivative of y is called x2, y is called x1, the derivative of y is called x2, and the derivative of y, so the second derivative of y is called x3, and so on. The thing is, we assume, so these variables x1, x2 and x3, these are called the state variables, okay? Just keep the names in mind. I'm going to explain why they are called state variables, okay, soon. So these are called the state variables, okay? And that's why, based on this, the name is state variable modeling technique, or rather state space modeling technique. These variables x1, x2, x3, these are called the state variables, okay? And you might now try to understand some important ideas behind this. Maybe this differential equation, imagine this differential equation is relating to a mechanical system, right? A mechanical system, and in which y is representing displacement. And if y is representing displacement, then y dot is representing velocity, then y double dot is representing acceleration, then y triple dot is representing jerk, right? So that way, we have certain mechanical things, mechanical variables that are associated with the differential equation, right? Namely, displacement, velocity, acceleration, and jerk, right? And you see that the state variables represent some of them already, right? x1 is representing the displacement, x2 is representing the velocity, x3 is representing the acceleration. So actually, if you think about it, you see that the state variables help us describe certain internal behavior of the system, right? Just hold on. All right. So please make sure to ask questions that you might have at this point. I'm not sure how much you are understanding what I'm saying here. Okay. So these state variables describe the behavior of the system internally, right? Now let's substitute these into this. So the substitution will be happening into this, right? So let me just copy this differential equation here. And think about what we can substitute, right? Think about this y. This y now becomes x1. Now there is y dot, that becomes, y dot is x2. So let me write x2 here. Then we have y double dot, and that's x3. And then we have y triple dot. Now, of course, I don't have any y triple dot here. But y triple dot is like x3 dot. Now, there might be a very important question coming from one of you, and the question might be that why don't I assume x4 and assume it like y triple dot and put it here? We could do that. But this is not necessary. Okay, this is not necessary. We shall soon see that the number of state variables should equal the order of the system. So this is a third order system. Okay, this is a third order system. Okay, and the number of state variables we assume should be equal to the order of the system. So we are assuming 3 state variables. and that's sufficient. We could assume x4, but that won't be required. Okay, but that's sufficient. So that is the differential equation. Now, if you look very carefully, we can actually do some simplification on this as well, and look very carefully. Okay, so we are writing a3 x3 dot, and that equals minus a0 x1 minus a1 x2 minus a2 x3 plus b0 u. And then we can actually divide everything. And now we can actually divide both sides. We can actually divide both sides by a3, right? So that way I'm going to have x3 dot, and that becomes minus a0 by a3, a0 by a3 x1 plus a1 by a3 x2, so not plus, I mean minus, minus a2 by a3 x3, not x3, yeah, x3, not a problem, I hope, yeah, and plus b0 by a3 u. Okay, but look at this differential equation. If you don't see anything, but just look at this differential equation, what kind of differential equation does it look like? Is it a second order differential equation? Is it a third order differential equation? Or is it a first order differential equation? The answer is, it is a first order differential equation, because there is just one derivative term associated with this, right? So we are successful, but we are not all the way through this, right? So we have converted this differential equation into one differential equation that looks like this. Okay, so let me write that down. Okay, so that's the differential equation that is actually describing the whole system, but not exactly, right? Not exactly, because these x1, x2, and x3, these are not so innocent, right? These are also very nicely defined. That's why we have this first order differential equation, right? So because these are not so nicely defined, let me just define them right away here. So what is x1 dot and what is x2 dot? We know that x1 dot is x2 by very definition here. We say x1 dot is equal to x2 and x2 dot is equal to x3, right? So let me just write those down. x1 dot is equal to x2. So here, let me write it down here. And x2 dot is equal to x3. Okay, this is how we write it to make sure that this is in a standard shape. Okay, but these three differential equations taken together describe everything regarding this differential equation. So this differential equation is equivalent to this set of differential equations, right? Because here we have all the conditions that we imposed earlier. So these are the conditions that we imposed earlier. Okay, and this is the final differential equation describing the system. So that way, these three differential equations right now are all first order differential equations. Notice very carefully. These three differential equations are all first order differential equations, and taken together, these three differential equations construct what is called the state space model. But not yet. We actually describe this in the form of a matrix. And you might see that is why we have actually written it this way, because here we can say this is like 0x1 plus 1x2 plus 0x3 plus 0u, something like that. Then we can say 0x1 plus 0x2 plus 1x3 plus 0u, yeah, sort of like that. So if we now write it that way, we can actually convert everything into the form of a matrix, right? So these, now let's construct a matrix out of this. So I have x1 dot here, x2 dot here, x3 dot here, and on the right hand side, right? So here I would have a 3 by 3 matrix. Okay, and there I would have x1, x2, x3, I believe you understand how to do matrix multiplication. And there I would have a 3 by 1 matrix and multiplied with u. All right. Now let's put the values here. Okay. Let me just. All right. Let's put the values here and see how that works out. So x1 dot is equal to 0x1 plus 1x2 plus 0x3. Right. So 0 times x1, 0 times x1, 1 times x2, 0 times x3. That works. For the next one, I have 0, 0, 1 here. And for the next one, I would have minus a0 by a3, minus a1 by a3, minus a2 by a3. And on the right hand side, I would have 0, 0, b0 by a3, right? So this is called the state model of the system. Okay, this is called the state model of the system. Okay, this differential equation. Now I'm calling this a differential equation, not differential equations, because now we can assume something very important. Okay, say assume this, that we have, so this is a representation where we put an underline behind under a variable, right? That indicates that this is no longer a scalar quantity, but it is a vector or a matrix quantity. Now here I am assuming that this vector quantity is representing x1, x2, x3, right? All right. And what is the derivative of this vector quantity? The derivative of this vector quantity is just x1 dot, x2 dot, x3 dot. Okay, not a problem. Now if we do so, and if we put certain names into these matrices, let's say we call this matrix, all right. So now you see that if we now do this, and here let me just, all right, so here if we assume this matrix to be a matrix A, let's name this matrix A, and assume this matrix to be matrix B, then we have a differential equation that relates then we have a matrix differential equation, right? Because you see that this is x dot, right, derivative of this vector quantity, right? And this is just x, right? And this is of course u. So that way this very differential equation actually becomes x dot, paste it down here, this differential equation becomes x dot equals a x plus b u, right? So x dot equal to ax plus bu, where x is this x1, x2, x3, x dot is x1 dot, x2 dot, x3 dot, right? and of course A and B are given like this, and U of course is the input. So this is called the system equation or the state equation. Okay, this is called the state equation. Let me just write it down. So this is called the state equation. Okay, and what about the output of the system? What about the output of the system? The output of the system, look back. What is the output of the system? The output of the system was this, because you notice that we assumed y to be equal to c. Okay, and what was y? Y was just x1, right? If y was just x1, then what is the output of the system? We have to also represent that using the matrix form. So we can write y is equal to, you see here, okay, there is just one small problem here. Let me just get rid of this because I cannot right now describe this to you. Just put it as u, not a problem. We are going to use the property of linear time invariant systems later on actually to figure that out. We're simplifying the discussion right now. All right, and here the output is just, we know that the output of the system is just, and you know what, we can actually keep this, not a problem. Oh, sorry for that, we can actually keep this without any issue, right? We look at this, right? So we already considered that this is just the output, right? Because that is the definition, that is the very definition we assumed. And since we assumed this to be the output, we can actually say that the output is just x1, right? Let me just write it down here. So we can just say the output is just x1, right? Just x1. But now we try to understand that we want to describe everything in this vector matrix form. So we don't just write output as x1, but instead we try to understand that writing this way is not a feasible option, because I have to now use these variables, these particular variables, right? State variables. So output is just x1, but we write it as 1x1 plus 0x2 plus 0x3. And that way we simply have this sort of expression here, 1 0 0, and there we have this x1 x2 x3, and where this x1 x2 x3, this matrix is essentially x, right? So therefore this equation becomes y is equal to 1 0 0 times x. Notice carefully. So that actually this this here, this is called the matrix C. Often this is written as matrix C. Okay, so now this is C times x, and this equation represents the output. So this equation is called the output equation. Okay, this might seem slightly what should I say, slightly not simple, or rather it might seem on the first to go, it might seem very difficult to understand right now, but we are going to solve problems right now, and that way we are going to actually see that this is not a very difficult thing to actually follow, right? This is not a very difficult thing to follow. Let's just see an example, and it'll be very easy then for you to actually see. Okay, example. Okay, let's say we have a system that has a transfer function. Okay, let's say we have a system that already has a transfer function. Okay, so a transfer function, let's say the transfer function is, let's say 1 by s cube plus 5s square plus 2s plus 7, and let's put 3 here. Okay, not a problem, right? So from there, question is construct a state space model for the system. Notice the English here. We are saying construct a state space model, not the state space model, because there is no the state space model. Okay, a same system can be described with infinitely many different state space models, and they all describe the same thing somehow. Okay, and we are going to actually prove that in a later class. Okay, so now let's solve it. Okay, solution. How we actually convert this transfer function into an equivalent state space model. Okay, let's see that this transfer function GS, which is nothing but the ratio of the output to that of the input under zero initial conditions, is this. It's 3 by s cube plus 5 s square plus 2s plus 7. Right? Okay, right? Not a problem. And so we can actually do a reverse calculation here. So we can write s cube ys plus 5 s square ys plus 2s ys plus 7 ys, and that should be equal to 3 x's. Okay, right? And of course, if I now go back to the differential equation, we can actually do that, right? Because this is now simply denoting that this is y triple dot t, right? And this is simply denoting 5y double dot, plus this is denoting 2y dot, and this is denoting 7y, and this is just 3x, right? Right? Or rather, let me just use the proper naming schemes here. We are just calling this to be u, because that is the proper naming scheme here. Okay, the input is considered to be u, so that way we have better representation here. All right, now we have the differential equation describing the system. Now once we have the differential equation describing the system, we can now assume the state variables. So we now know that the state variables are going to be, or rather, let me just define the variables. So you know already u is the input, not a problem. We already know y is the output, that's also not a problem. And just define the state variables. Define state variables. So we are saying that x1 is a variable that is representing y, x2 is a variable that is representing y dot, which is in turn representing x1 dot, and x3 is a variable that is representing y double dot, which is in turn representing x1 double dot, which is just x2 dot. Okay, let me just write down x2 dot. That would just be fine. And since it's a third order system, these three are sufficient, right? And let's put this in this differential equation, right? If we do that, then of course the first thing that we have, y triple dot, that simply becomes x3 dot. Then we have 5y double dot, and y double dot simply is x3. Then we have 2y dot, and that simply is 2x2. And then we have 7y, that's just 7x1, and that's just equal to 3u, right? 3u. And from there we can actually pretty easily construct the state space model, right? Because here we just need to write two more equations on top of this. Okay, the differential equations are, so from this we can actually, hold on. So this differential equation easily becomes x3 dot equals minus 7x1 minus 2x2 minus 5x3 plus 3u. All right, so that's the differential equation. And of course we have two more differential equations, and those two more differential equations are pretty easy to write already, because that's what we assumed earlier. And we assumed that x1 dot is just x2 and x2 dot is just x3. So taken together, these differential equations simply become x1 dot, x2 dot, x3 dot, okay, equals this equals 0, 1, 0, 0, 0, 1, -7, -2, -5, and then we have this x1, x2, x3. Then we have plus 0, 0, 3 u. That's the state equation, but I don't want to write it this way. Okay, so here we had x1, x2, x3, and that is just x, right? And here we had the derivative of x1, derivative of x2, derivative of x3. That was just the derivative of x, where we know that x is defined as the state vector. So this assumption, this name is known as, this thing is known as the state vector. A vector is a vertical, a column matrix, okay, where you have the state variables. So this state vector has the state variables in it. So it's a n cross 1 matrix. So here in this case, it's a 3 cross 1 matrix. Okay. So this 3 cross 1 matrix is actually describing this. So here we have the state vector, and this is the state equation for the system. This is the state equation. Okay. And similarly, what is the output equation? The output equation is very simple. We know that the output is just x1. Okay, just x1 is the output because that is how we defined it. Notice very carefully. The output is just x1. And of course, x1 is just 1x1 plus 0x2 plus 0x3. And that's how this becomes 1, 0, 0. And then we have x1, x2, x3. Okay, and that simply becomes 1, 0, 0, and x, right? Because this is the x vector, right? The state vector. So that way, we just have this as the output equation. Output equation y is just, output y is just 1, 0, 0, x1, x2, x3. But once again, instead of writing all these, we can just write the vector, name of the vector, and that is the state vector. Okay. And these two equations together describe the system. This is the output equation. All right. And sometimes we also have one more parameter here. We are going to discuss that in a future class. But this is the state space model of the system. This model accurately describes the system that we had the transfer function earlier. Okay, so we had a transfer function, but this model accurately describes the transfer function as well. Okay, and there are a few things that we have to understand and remember right now, is that these have particular names in them. So this model pretty much looks like this. You see, this model pretty much looks like this. The state equation looks like a differential equation that is of the form x dot is equal to ax plus bu. Okay, notice very carefully that we are putting underlines to indicate that these are either matrices or vectors. But this is very similar to something like a first order derivative, x dot equal to ax plus bu. Something sort of that, like that, right? So since this is sort of like a first order derivative, first order differential equation, we can apply certain standard techniques. Okay, and that's how this is so easy to use in a computer program. Okay, much easier than using your transfer function techniques. Okay, and of course the output y is c times x, plus there is another term d times u, which we are going to actually describe in a future class, and this will come up in a future class. Okay, so let me just tell you the names of all these things. Okay, you already know that this equation is known as the state equation, and you already know that this equation is already known as the output equation. Okay, all right. This matrix, so you already know what is x and what is x dot, right? X is known as the state vector. Okay, x is known as the state vector. So this is the state vector. So obviously x dot is the derivative of the state vector. A is known as the system matrix. It actually describes the behavior of the system. This matrix A determines the stability of the system, determines many other standard behaviors of the system. And this will be evident in the future, not right now. Now what about B? You see, U is the input, right? U is the input, and this matrix B, this is the matrix B. This matrix B actually brings the input to the system. So this matrix B is known as the input matrix. Matrix B is known as the input matrix. Input matrix. And similarly, this U is just the input vector. That's the input, right? This Y, we already know, that's the output.
7.
Right? This U is once again the input, so maybe just write it once more. Same input, okay? These are not different things. Now, of course, this is also the same state vector here. Right? C, now what is C? So you see, this is the state vector, okay? And this state vector is now being represented as output through this matrix. This state vector is being represented as output through this matrix, right? So this matrix is known as the output matrix for that reason. This is called the output matrix. Okay, and D, notice very carefully, this D, if it actually exists, it would appear like something like this. Okay, this will actually relate this input directly to the output. Okay, so when something directly goes to the output without actually going through the system, okay, then that's called a feed forward. Okay, if something goes directly to the output without actually going through the system, it's called a feed forward, and that's why D is sometimes called the feed forward matrix. Feed forward matrix. Okay, so these are the standard nomenclature regarding the state space modeling. Okay, all right, so we describe everything like that. So this is the same model, x dot equal to ax plus bu, and our output equation is y equal to cx plus du. D is 0 in this one. So in order to describe the state space model in a computer also, we just need to describe the matrix A, matrix B, matrix C, and matrix D. And if I describe matrix A, B, C, D, then we have a complete state space model, right? Do you understand what I'm saying? If we have the matrix A, B, and A, B, C, and D, okay, then we describe the state space model, because all the state space models for all linear time invariant systems, okay, would have this matrix A, matrix B, matrix C, matrix D, and the rest of the equation would look like just this: x dot equal to ax plus bu, y equal to cx plus du. We need to know A, B, C, D. So if we know the A, B, C, D, these matrices, that would describe the state space model accurately, exactly, right? So sometimes when you are actually using a computer program, we are going to do that in one of our future classes. There you actually describe the system by just defining the matrices A, B, C, and D. Once you define the matrices, you just have the system with you present, okay, by just having the matrices, right? And in fact, there are programs that can convert transfer function models to state space models and state space model to equivalent transfer functions, and those state space models will just require you to have this A, B, C, D, nothing else, okay, because the rest of the equations are the same. You now see why this is so systematic, because I can give you any system and that system will be described using this systematic way: x dot equal to ax plus bu, y equal to cx plus du, using these two equations. Except for the fact that A, B, C, D, these will have different values regarding the example, but you understand that these would always be represented in this form. Okay, the differential equations are always going to be represented in this form. Okay, all right, time for another example, and there we're going to actually end the discussion here. Maybe 2 or 3 more examples, I guess. Let's take a second order example. Another example. Say the transfer function is say 7 by 2s square plus 5s plus 1, let's say. All right, that's not a problem, right? So convert it to a state space model. That's the question. Okay, so what is the solution? Of course, we know that the ratio of the Laplace transform of the output to that of the input is given by this 2s square plus 5s plus 1, and now of course do cross multiplication on this, so that's going to be 2s square ys plus 5s plus ys, and on the right hand side I have 7xs. Now take the inverse Laplace transform assuming zero initial conditions and all, so that way we're going to have 2y double dot, this is again time domain, right? So this is a function of time, right? And then this becomes 5y dot, this is plus y, and this is 7x. Okay, now not x exactly, I'm sorry, because this has to be u. All right, and of course assume state variables. Now here I am going to have two state variables. Just hold on, we're going to have two state variables, of course, since it's a second order system. So x1 and x2, and as the nomenclature goes, x1 would be rather x1 is just going to be y, okay, and x2 is going to be x1 dot, which is in turn y dot, not a problem, right? So these are the two state variables declarations, right? Now we can actually convert this differential equation very easily, and that way this becomes 2, of course y double dot is just x2 dot, so x2 dot, that becomes 2x2 dot plus 5 y dot becomes x2, and y is just x1, and this is 7u, not a problem, right? And of course that's the differential equation. From there we need to actually simplify this, so that way this becomes 2x2, that is minus x1 minus 5x2 and plus 7u, and of course I can bring this 2 here, that becomes half 5 by 2, 7 by 2. All right, so sorry, x2 dot I mean right? And of course we need one more differential equation to describe all of it, so let's bring this here, and the other differential equation that needs to be described is x1 dot, and that's x1 dot is just x2, because that's how we defined it, x1 dot is equal to x2. Now these two differential equations are describing the actual original differential equation without any ambiguity here. Okay, so this can now be described in the state space technique as x1, x2, both of them have derivatives here, and here we have zero, 1. Notice this is minus half, this is minus 5 by 2, and this is plus 0, 7 by 2 u, and that's a state model. Okay, or that's the state equation. You can call it whatever you want. And what is the output equation? The output equation is very simple. That's going to be y, which is equal to x1. So the output equation is simply, if this is just y equal to x1, let me just bring this here. Okay, that's going to be simply y is equal to 1, 0, 0, and obviously, I'm sorry, here I had to have something. x1, x2, the state vector here. Similarly, I have x1, x2. All right. So this is once again a very similar representation, right? Because there you can write, therefore the model is x dot, which is the derivative of the state vector, and that's equals 0, 1, minus half minus 5 by 2, minus half minus 5 by 2, and then x, which is the state vector, plus the input matrix 0, and it was 7 by 2. It was 0, and this was 7 by 2. Okay, and this was just u, and the output is y is equal to 1, 0, 0, x. And of course, you could write plus 0 u to make sure that this is like in the form. So this is the total state space model. Okay, this equation is the state equation, this equation is the output equation. Here matrix A is this matrix, matrix B is this matrix, matrix C is this, matrix D is this. So A, B, C, D, these four matrices are now describing the system. Okay, so this is the state space model. Let me right now do one thing. Let me just bring this, let me just keep this here, and let me bring down the transfer function. Let me bring down the transfer function. I want you to see some useful things about it. So that's the differential, that's the transfer function, right? I want you to see some patterns in it. Okay, you see there was a 7 here, and where do you see that 7 go? Right, this was 7 by 2. That 7, where did it go? That went here, right? All right, you see a 1 here. Okay, where did that go? That appeared here. Notice very carefully. Okay, I don't know how much you can actually distinguish these colors. Not entirely sure though. This is sign. This is minus 1, 1, right? That is by 2. All right, and you see these 2 everywhere. Let's use this ink. So this 2 everywhere. So this 2 is actually here, also here, also here. The point I'm trying to take home is that you can actually look at a transfer function and construct the state space model yourself without doing much of any calculation. I'm sorry, let me use a different ink. Which ink should I use? Maybe red. All right, right. All right. So now if I give you another transfer function, another second order transfer function, right? You should be able to construct the state space model by just looking at it. Okay, let's try that. Once we have that, so once you understand the pattern, okay, you can actually do these things pretty easily. Okay, so now how these things are useful, how to use this, we are going to learn that in the next class. So that won't be a problem. So let me just say this is 10 divided by 3s squared plus 7s plus 2. Okay, right. Somebody please tell me what is going to be the state space equation. So let me just try x dot equal to ax. Now what is a? I don't know. Plus bu. What is b? I don't know. I have to put the values, right? And y is equal to cx plus du, which is now, of course I know that's going to be 0u, not a problem. Now once we understand the pattern, we can actually write down this pretty easily. So let's write 0, let's write 1. Okay, let's put a minus sign here, and we can actually, you can, I should rather suggest you go back and try to do this the way we did it, right? Try to do this the way we did it and make sure that it actually, you get the same result. Okay, that way you would understand that you know the modeling technique properly. All right, hold on. So we see that this is going to be from here, let me just once again use a different inking here. All right. So that's gonna be 2 by 3. That's gonna be 2 by 3. Okay, and in fact everything would have that by 3 here. Let me just put that here. Okay, I would have a 0 here. I'm just matching the pattern here. So I would gonna have a 10 here, and there is going to be a 7 here, of course with a minus sign, I mean. Okay, and the rest is going to be not 1 0 0. Did I add 3 zeros? I'm sorry. I don't think any of you are actually properly following, because none of you could figure that mistake out. Okay, there are no 3 vectors here, just 2, right? All right, that's gonna be just 1 and 0 here. That's the state space model, complete state space model for this. So I would request you to actually try to figure this out yourself and make sure that the calculations are correct. Okay, so rather I should say this is one of the possible state space models for the system. Okay, so in a similar fashion, let me bring that third order system. So we did this thing multiple times. So let me bring the third order system here. What was the third order system? So that you get the pattern. Okay, my objective is to make sure that you can do these things easily as possible. Okay, so this is the state space model, right? And this was the transfer function. So here we had a 1 here. Okay, so now let me just make sure that you see this thing properly. So this was 1 here. That's why we got some simplification here, but this 1 actually gets divided everywhere. So this is 7 by 1. Okay, so let me just write it down. This is also like 3 by 1. Okay, and you can actually see where these ones actually came from. Those one are belonging to those. Right. All right, so where did this 7 come from? What is this 7? Is this? Okay, you see, this is again a very simple thing to do. Once you understand the approach here, you don't even have to do any calculation. I should say you don't even have to do any calculation, because you can do this pretty easily then. Okay, this 5, this 5, let me give it. Okay. Okay, what about this 3? Okay. All right, so that is something you can see properly, right? So again, constructing the state space model is not a very difficult task, but there are many other different types of systems, and we are going to actually describe those in one of our future classes. But here is your exercise problem for at least for today. Okay, the exercise problem is that you need to construct a state space model for the system with the transfer function okay. So please do that as your exercise problem. Of course, you can actually match the pattern and do this, but I would rather suggest you go in the standard way, the way we have discussed so far, and then try to make sure that the pattern actually matches. Okay. Once, once you do that, in the next class, we are going to actually dive deeper into this and see how state space modeling can be done for slightly more complicated systems. And from there, we shall find out a standard way in which you can actually go back to the transfer function models as well. And then we're going to actually solve the state equation, because I said earlier that this equation, this set of equations, right? This very simple thing, okay, this x dot equal to ax plus bu and y equal to cx plus du is so systematic that you can actually develop algorithms. Okay, so if you want to construct a controller, I can actually develop an algorithm in which you can actually tell, okay, if this is so, or if these are the parameters, then do this, sort of like that, which is not possible in the transfer function approach. Okay, in the transfer function approach, we often do some ad hoc techniques, we often employ some ad hoc techniques and try to figure things out as we proceed. But here we can pretty much develop algorithms, and that can actually bring out very powerful and very useful controllers. Okay, and there are certain other things that are not just controllers. There are certain things called observers, okay, which you don't yet know what it means. Okay, but those things can be done through state space. But in fact, I told you earlier, just once again to recap, as a modern in current day and age, in present day and age, if you are a control system engineer, or if you're doing anything regarding control systems, it is, you can almost be certain that you are not going to use transfer function approaches. Or at least for the most part, you are not going to use transfer function approaches. Rather, you're going to use the state space approach. That's the modern control technique. You want to design a controller for a robot, you probably are going to use the state space model. Okay, not the transfer function model. Okay, you want to create some automation. Yes, you're going to probably use the state space model, not the transfer function models. Sometimes we do use the transfer function model in some scenarios, especially in process control. Okay, because there are certain types of controllers that are so tried and tested, and these are so useful, even though they are not perfect, but they are so useful and they are so well tested over the decades. So we actually, over the decades, these controllers have been so used and so tested, like something called the PID controller. And when you want to model a PID controller, design a PID controller, you need a transfer function model. So under those scenarios, you use transfer function models. Okay, but there are modern controllers which are superseding those. Okay, in any case, this is the modern control engineering. So we are starting modern control engineering. So we would end a reasonable portion of this, and we will complete a reasonable portion of this on the modern control aspects, and then we are going to go back to the classical control where we discuss transfer functions. All right, so in the next class we shall learn how to deal with slightly more complicated systems, maybe systems, not just maybe, but of course with systems that probably have something like this, a transfer function that are slightly complicated than this. Okay, okay. So that is something we are going to discuss in the next class. And in the next class, we are going to learn how to, in general, convert state space models into equivalent transfer function models. Okay, transfer function models. And then we're going to solve the state equation. All right. Then we're going to find a technique in which you can solve the state equation, because you see that this is just one differential equation describing everything. This is the differential equation. This is just an algebraic equation, right? This is not even a differential equation. So you're going to learn those techniques. I hope you, I don't know whether you have any questions or not, but I will just give you 1 minute to ask any questions. And then we're going to end the discussion, right? So thank you for being here. Please ask any questions that you might have. All right, so thank you very much. I will see you on the next one.